Welcome to class number 28 of basic electronics. So we are discussing the MOSFETs and we are discussing on some problems. So we'll do a few more problems actually today. So let us consider this circuit. So this is basically a voltage divider biasing circuit for MOSFETs, but instead of this point connected to the ground, this point is actually connected to minus 5 volt source, and this upper point is connected to plus 5 volt source here. And we have this resistor magnitudes as Rd equal to 1.2 kilo ohms, the resistance which is connected to the drain, so 1.2 kilo ohms. Rs is 0.5 kilo ohms, the resistance which is connected to the source, and R1 is 14 kilo ohms. So R1 and R2 are the biasing resistors, so 14 kilo ohms over here, and then R2 is 6 kilo ohms, so 6 kilo ohms over here, and the voltage at this point is basically Vg. Okay, and we are asked to find out Vgs, the drain current Id, and Vds. So these three parameters we have to basically find out. Okay, and it is also given that for the MOSFET W by L equal to 25, and the small k in dash, which is the process conduction parameter, or small k in, which is the process conduction parameter, is basically 25. So we are provided with this info and we are asked to find out the value of VGS, ID and VDS. Okay, so let us find out the conduction parameter first. So we know that capital Kn is equal to mu n C ox W divided by 2L, and the small kn or kn dash is basically the process conduction parameter, which is mu n C ox. So capital Kn and small kn are basically related by this equation. Capital Kn equals to small kn W by 2L. So we know the value of small kn and we also know the value of W by L. So this basically becomes equal to 75 into 25 divided by 2 microampere per volt square. Okay, so this Kn, small kn, is microampere per volt square. Now let us find out this gate voltage, the value of the voltage at this point, Vg. So we know that no current actually flows into the gate, so the current only flows through these resistors R1 and R2 in this direction, and therefore the voltage at the gate Vg can actually be given by the equation R2 divided by R1 plus R2 into 5 volts plus R1 divided by R1 plus R2 into minus 5 volts. So we have actually used the superposition theorem here. If you do not know what this theorem is, you can still calculate the voltage Vg. So the voltage Vg, you have to calculate the current. So the current is basically 10 divided by R1 plus R2, 10 which is 5 minus of minus 5 divided by R1 plus R2, that is the current, and once you find the current, you can also find the voltage at this point Vg. Okay, that is the normal way. So here I am using the superposition theorem. So R2 divided by R1 plus R2, so 6 divided by 6 plus 14 into 5 volts plus 14 divided by 6 plus 14 into minus 5 volts. So this basically gives me minus 2 volts over here. Okay, so minus 2 volts. Now what is the value of the voltage at the source? So let us call this voltage as Vs, which is the voltage at the source. So what is the voltage at the source? So the voltage at the source Vs is basically equal to minus 5 volts plus the voltage drop across this resistor Rs. So the voltage drop across this resistor Rs is basically Id times Rs, and Rs is equal to 0.5 kilo ohm. So minus 5 plus 0.5 Id, where Id is actually in milliamperes. Okay, volts. Okay, so this is basically the source voltage. So when we calculate VGS, VGS is basically equal to Vg minus Vs, and Vg is equal to minus 2 volts. Vs is equal to minus 5 plus 0.5 Id. So this basically becomes 3 minus 0.5 Id. Okay, so this is basically the value of VGS. Okay, now in the same case, or as the same case of the previous problems, we do not know whether the MOSFET is actually operating in saturation or in triode. So initially we have to make an assumption, and if that assumption is not valid, then we would get a contradiction at the end. Okay, so let us initially assume that the MOSFET is in saturation. So let us first assume that the MOSFET is operating in the saturation regime. So if the MOSFET is operating in the saturation regime, then the current is given by ID equals to capital Kn VGS minus VTN whole square. Okay, now VTN for this MOSFET is given by 1 volt. So I have forgotten to write this here. So VTN for this MOSFET is basically 1 volt. Okay, so VGS minus VTN, and Kn, as we calculated earlier, the value of Kn is basically 75 into 25 divided by 2 microampere per volt square, and this is basically equal to 937 microampere per volt square. And this is basically equal to 0.937 milliampere per volt square. Why I am converting this microampere to milliamperes is because I have assumed in all these equations over here that ID is in milliamperes actually, and that's why I could actually multiply it with 0.5 kilo ohms to get volts. Okay, so that is why I am converting this microampere to milliamperes, because the ID or the drain current that we would be getting in milliamperes. So just to match dimensions, we are just using milliamperes over here. So 0.937 into VGS is 3 minus 0.5 ID, and VTN, as we discussed earlier, it is given to be 1 volts over here whole square. So this becomes equal to 0.937, and this is 2 minus 0.5 ID whole square. Okay, so now we just break this quadratic equation over here, and we basically get 3.748 minus 1.874 ID plus 0.234 ID square. So this is equal to this drain current ID. So we just shift it to the left hand side and we get ID square, and we divide it by the appropriate factor basically to actually get the coefficient of ID square to be 1. So ID square minus 12.28 ID plus 16.01 equals to 0. Okay, so ID is basically equal to 12.28 plus minus root over 12.28 square minus 4 into 16.01 divided by 2. Okay, so this is equal to 10.79 milliamperes. 10.79 milliamperes is for the plus sign over here, and we get another answer for the minus sign, which is 1.48 milliamperes. Okay, now like before, we have to check which one is actually the physically possible solution. Okay, these two are mathematically valid solution, but we have to check which one is the physical solution. Okay, so we have ID equal to 10.79 milliamperes and 1.48 milliamperes. Okay, now VGS, as we calculated earlier, VGS was equal to 3 minus 0.5 ID. So if ID is equal to 10.79 milliamperes, then VGS is equal to 3 minus 0.5 into 10.79 volts, which is approximately equal to 3 minus 5.4 volts, which is basically equal to minus 2.4 volts. So VGS is negative and VGS is also less than VTN. So if VGS is less than VTN, then this means the MOSFET must be in cutoff, which is not valid in this case. In this case, the MOSFET is conducting current, so it is not in cutoff, and it must be in either the triode regime or the saturation regime. So now let us check if the condition of saturation is actually valid. So to check the condition of saturation, we have to calculate the value of VDS. The condition for saturation is actually VDS greater than VGS minus VTH. So this is the saturation condition. And we have to check whether this condition is valid or not. Okay, so to do that, we have to first find out the value of VDS. So from this figure over here, VDS is basically equal to this 5 volts minus the voltage drop across this resistor RD. So 5 volts minus IDRD. Okay, so VDS is basically 5 volts minus IDRD, and RD is equal to 1.2 kilo ohms. Okay, and ID, we have checked that ID equal to 10.79 milliamperes is actually not a valid physical solution. So ID must be equal to 1.48 milliamperes. Okay, because 10.79 milliamperes is basically not a valid physical solution. Okay, so VDS is basically equal to 5 volts minus ID is 1.48 milliamperes into RD, and RD is equal to 1.2. Okay, 1.2 kilo ohms. Actually, there is also a voltage drop across this resistor Rs over here. So VDS is basically equal to this voltage. VDS is basically equal to 5 volts minus of minus 5 volts, which is basically the potential difference. So the potential difference is 5 volts minus 5 volts. Potential difference is basically 5 volts minus 5 volts, which is equal to 10 volts. So this potential difference 10 volts minus the voltage drop across this resistor Rd minus the potential drop across this resistor Rs. Okay, so VDS is basically equal to 10 volts, okay, minus the potential drop across this resistor Rd minus the potential drop across this resistor Rs. So let us write the equation accordingly. So VDS is basically equal to 5 volts minus 5 volts. So this is the potential difference minus the potential drop across the resistor Rs minus the potential drop across the resistor Rd. Okay, and Rs was basically 0.5 kilo ohms and Rd was basically 1.2 kilo ohms. So this is equal to 10 volts minus Id into 1.7 kilo ohms. So 10 volts minus 1.48 into 1.7 volts, and this is equal to 7.484 volts. Okay, so we have the value of VDS, and let us check if the saturation condition, that this condition VDS is greater than VGS minus VTH, if this condition is valid. Okay, so what is the value of VGS? So VGS is basically 3 volts minus 0.5 ID, which is equal to 3 volts minus 0.5 into 1.48 volts, 3 volts minus 0.74 volts. So this is equal to 2.26 volts. Okay, so VDS greater than VGS minus VTN is actually valid. So the MOSFET must be in saturation. So we have actually done the correct assumption by assuming that the MOSFET was operating in saturation. Okay, let us write down the final answer here. So the final answer is VGS is equal to 2.26 volts, VDS is equal to 7.48 volts, and the drain current ID is equal to 1.48 milliamperes. So this is basically our final answer. So now let us go to the next problem. So here we have a MOSFET which is biased with a drain resistor RD equal to 10 kilo ohms. The source is connected to the ground and the gate is connected to a input voltage Vi. Okay, and V0 is the voltage taken at the drain. So this is our circuit, and the information that is given to us is VTN equal to 0.8 volts. The threshold voltage is equal to 0.8 volts, and small kn dash, which is the process conduction parameter, is equal to 30 microampere per volt square. Okay, so these two information is given to us, and we are also given that V0 is equal to 0.1 volts when Vi is equal to 4.2 volts. Okay, and you are asked to find out W by L for the transistor. Okay. So first in this problem, look at the information that is given. You are given with the threshold voltage. You are given with the small kn but not with capital Kn. So small kn times W by L divided by 2 is equal to capital K, and you are given with this information V0 equal to 0.1 volts when Vi is equal to 4.2 volts. Okay. Now from this information over here that V0 is equal to 0.1 volts when Vi is equal to 4.2 volts, we can readily determine the drain current. Okay. So the drain current ID is also equal to the current that is flowing through the resistor RD. So ID is equal to so here the voltage VDD is equal to 5 volts. Okay, so ID is basically equal to VDD minus V0 divided by RD. So VDD is equal to 5 volts and V0 is equal to 0.1 volts, and RD is basically equal to 10 kilo ohms. So then this is equal to 4.9 divided by 10 milliamperes, which is 0.49 milliamperes. So this is basically the drain current ID. Now VGS, so VGS is equal to VI because the input voltage is fed directly to the gate of the transistor. So VGS is basically equal to VI, and VI it is given that in this case this is equal to 4.2 volts. So VI is equal to 4.2 volts. Now the first thing to check is that whether this MOS is in saturation or whether this MOS is in triode. Okay, so VDS here is equal to V0, which is equal to 0.1 volts, and VGS minus VTN. So VGS is equal to 4.2 volts, VTN is equal to 0.8 volts. So this is equal to 3.4 volts. So VDS is basically less than equal to VGS minus VTN. So the MOS is basically operating in the triode. Okay, so the MOSFET is basically operating in the triode regime. So we have to use the equation of the triode regime here. So let us write the information that we have. We have VGS is equal to 4.2 volts, VDS is equal to V0, which is equal to 0.1 volts, and ID is equal to 0.49 milliamperes. Okay, so the equation of the triode regime of the MOSFET is equal to ID equal to capital Kn to VGS minus VTN, VDS minus VDS whole square. Okay, so this is equal to capital Kn 2 times 4.2 minus 0.8 volts into VDS is 0.1 minus 0.1 square. So if I simplify this, I get 0.67 volt square. Okay, so this is basically volt square, square of the volts. So capital Kn into 0.67 volt square. Okay, now ID is equal to 0.49 milliamperes. So in this side over here we write it as 0.49 milliamperes. So Kn is equal to 0.49 milliamperes divided by 0.67 whole square, which gives me 0.731 milliamperes per whole square. Now capital Kn is equal to small kn, the process conduction parameter, times W by 2L. (0.731 milliampere per whole square). So W by L is basically equal to 0.731 milliampere per whole square multiplied by 2 divided by small kn dash. Okay, now small kn dash is equal to, let us check this out, it is equal to 30 microampere per whole square. So 0.731 milliampere per whole square into 2 divided by 30 microampere per whole square, we would convert it into milliampere per whole square, because the unit here is basically milliampere per whole square. So just to match dimensions, we would convert this 30 microampere per whole square into milliampere per whole square. So 30 microampere per whole square is equal to 0.03 milliampere per whole square. Okay, so this is equal to 48.75. Okay, so this is what was asked in the question, that what is the value of the W by L for this transistor. So we have found out the value of W by L to be equal to 48.75. Okay, so this is the answer basically. Okay, now let us go to our last problem. So this is a design problem basically. We have a 10 volt source which is biasing our MOSFET, and through this resistor RD and R1 R2. So we have a resistor RD here, we have this MOSFET, and we have another resistor RS. This is grounded. Here we have RD equal to 5 kilo ohms. Then we have RS over here. Then we have the biasing resistors R1 and R2. Okay, and you are given that VTN equal to 1.2 volts and the process conduction parameter small kn dash is equal to 60 microampere per volt square. So this information is given, and you are asked to design the circuit that is, choose R1, R2 and RS along with W by L such that VDSQ is approximately equal to 5 volts and the current through R1 and R2 is approximately 5% of the drain current. Okay, and it is given that the voltage across RS is approximately equal to the gate to source voltage of the MOSFET. So these are the conditions that are given to you, and basically you have to design this circuit. Now the flexibility of this kind of problems is that you actually have to choose a starting point. You are given conditions that you have to fulfill. So here the condition is that the current through R1 and R2 is approximately 5% of the drain current. So this condition, basically this is one condition, and the second condition is that this VDSQ is basically approximately equal to 5 volts. So these are the two conditions that are given to you, and you have to basically design the circuit. You have to choose R1, R2 and RS, and you also have to choose W by L for this MOSFET. Okay, such that these conditions are satisfied. Now in this kind of problems, generally we assume initial conditions, so you have to break the loop somewhere because no information is actually given to you. So you have to make some choice actually. Okay, and you are actually free to make your own choice actually. So someone might choose the value of, for example, at the starting point, someone may choose the value of RS to be, let us say, 5 kilo ohms. Someone may choose it to be 10 kilo ohms. So basically like that. So you are given, or you get the opportunity to choose the value of the resistors, or one of the resistors at least. So here the information, the parameters of the design or the conditions of the design are basically given to you, and you have to basically choose this three resistors R1, R2 and RS. So generally if we choose one or two parameters of the circuit, you generally break the loop, and if you choose one or two parameters of the circuit, then the other parameters of the circuit are determined automatically. Okay, so basically like that. So in this problem over here, let us first use the resistors to write the equation for the current. So ID, the drain current, is equal to the voltage drop across the resistor RS, which is VRS, divided by RS. Okay, now VRS, it is given that the voltage drop across this resistor RS is approximately equal to VGS. So this is the condition that the voltage drop across RS is approximately equal to VGS for the MOSFET. Okay, so we just take this condition over here, and this is approximately equal to VGS divided by RS. Okay, so this is one equation, and we also have a second equation for ID, which is basically 10 volts minus VDSQ. So VDSQ is basically the DC drain to source voltage. Okay, the DC value of the drain to source voltage. So this potential difference basically. So here only we have DC voltages, we do not have AC voltages. So VDSQ is actually equal to VDS. So 10 volts divided by VDSQ, 10 volts minus VDSQ divided by RD plus RS. Okay, so 10 volts minus VDSQ is basically given as 5 volts. In the question it was given that VDSQ is approximately 5 volts. So 10 volts minus 5 volts divided by RD plus RS. So which is equal to 5 volts divided by RD is equal to 5 kilo ohms plus RS. Okay, so we are stuck in a loop here. We do not know what is the value of VG, the gate voltage, because we do not know what is the resistor R1 and R2. So we do not know what is the current. Okay, if we would know the value of VG, then we could perhaps find out the value of current by other methods, but we do not know the value of this R1 and this R2 over here. Okay, so, and since we do not know the value of the R1 and R2, we do not know what VG is, so we are kind of stuck in a loop. There is no way to actually calculate the drain current. Okay, so these two equations for calculating the drain current are also not very useful because we do not know the resistance RS. So what we do here is basically to break the loop, we basically choose the value of the resistor RF. So we choose a value of the resistor Rs. So we choose Rs is equal to 5 kilo ohms. This choice is basically dependent on your own, and you can choose Rs equal to 10 kilo ohms or 15 kilo ohms also, and depending on your choice the other solutions of R1 and R2 would also change. So here I am choosing Rs equal to 5 kilo, and depending on that I would solve for R1 and R2 and also for W by L. If you choose Rs equal to 15 kilo ohms on the other hand, you would get a different value of R1 and R2 and a different value of W by L. So basically this problem doesn't have a fixed or a unique solution actually, and the solution basically depends on the value of the parameters that you actually choose. Okay, so here we choose Rs equal to 5 kilo, and depending on this choice we would be solving for the other parameters in the circuit. So we choose Rs equal to 5 kilo, so ID immediately becomes, from this equation over here, ID becomes equal to 5 volts divided by 5 kilo ohm plus 5 kilo ohm, which is equal to 0.5 milliamperes. Okay, so ID is basically equal to 0.5 milliamperes. Now it is given that the voltage drop across the resistor Rs is approximately equal to the voltage VGS. So VGS is approximately equal to VRS, and VRS is equal to the drain current into Rs. So 0.5 milliamperes into Rs is 5 kilo, so this is equal to 2.5 volts. Okay, so VGS is approximately equal to 2.5 volts. Okay, now VGS is approximately equal to 2.5 volts. In the question it is given that VDSQ is equal to or approximately equal to 5 volts, and it was also stated that the threshold voltage is equal to let us see, the threshold voltage is basically 1.2 volts VTN. This equation over here, VTN is equal to 1.2 volts. Okay, so VTN is basically equal to 1.2 volts. So we can understand that VDSQ is already greater than VGS minus VTN, and so the MOSFET is basically in saturation. Okay, so note that this condition that the MOSFET is operating in saturation, this condition could also have changed if you have chosen the value of Rs to be very high actually. Okay, so if you choose the value of Rs to be very high, then perhaps this condition of the saturation regime of the MOSFET can also become the triode regime, but I am not exactly sure. I have to check with other values actually. So in this case, where we have chosen that the value of Rs is equal to 5 kilo ohms, in this case the MOSFET is basically operating in saturation. So we can write the drain current of the MOSFET ID equals to capital Kn, the conduction parameter, times VGS minus VTN whole square, which is equal to capital Kn. VGS is equal to 2.5 volts, VTN is equal to 1.2 volts square. So this is equal to 1.69 Kn. Okay, and the unit is basically milliamperes, because capital Kn is basically milliamperes per volt square. Okay, so milliamperes. Okay, so capital Kn is basically equal to ID. ID is equal to 0.5 milliamperes divided by, we would actually not write this milliampere over here. Instead, let us actually keep the unit of Kn confined to Kn itself. So we would not, what I did here is because that the unit of Kn is milliampere per whole square, and then here we have whole square, so I multiplied these two and written as milliamperes, but let us not do it. let us just confine the unit of Kn to Kn itself, so that when we actually do the problem, the unit of Kn actually comes out automatically on its own. So this 1.69, the unit is basically volt square, because we had square of the volts over here. Okay, so volt square. So this is equal to 0.5 milliamperes divided by 1.69 volt square, and this is basically equal to 0.295 milliampere per volt square. Okay, so this is the value of capital Kn. Now in this question, the value of this small kn is already given. Small kn is 60 microampere per volt square, and 60 microampere per volt square is basically 0.06 milliampere per volt square. Okay, so we have found out the value of capital K, which is equal to 0.295 milliampere per volt square. So capital Kn is equal to 0.295 milliampere per volt square. Small kn, which is the process conduction parameter, is basically equal to 0.06 milliampere per volt square. Okay, so we have the equation Kn dash divided by 2 W by L is equal to capital Kn, which implies that W by L is equal to capital Kn divided by small kn dash multiplied by 2. Okay, so this is equal to 0.295 divided by 0.06 multiplied by 2, which basically gives me 9.833. So we have the value of W by L for this MOSFET, which was also asked in the question. W by L is equal to 9.833. Okay, note that if we would have chosen a different value for RS, the value of W by L would basically come out to be different, because in that case the value of the drain current would also be different. Okay, so once we actually choose one of these parameters, just as I said, that we break the loop and we automatically determine the other parameters of the circuit as well. So we have solved for two parameters till now. We have chosen the value of RS, and depending on the value of RS, we have solved for the value of W by L. So we have two parameters of which are asked in the question, and the next thing is actually to find out the value of R1 and R2. So now it is given that the current through R1 and R2 is basically approximately 5% of the drain current. So the current through R1 and R2, which we write as IR1 comma R2, is equal to 5% of ID, which is basically 5 divided by 100 into ID, the drain current, which is basically ID divided by 20. Okay, so now we also know the value of ID. ID is equal to 0.5 milliamperes, and divided by 20, so this gives us 0.025 milliamperes. Okay, so the current through the resistor R1 and R2 is equal to 0.025 milliamperes. Now we also have another equation for R1 and R2, which are basically dependent on the resistors R1 and R2, and this is basically equal to this 10 volts divided by R1 plus R2. So remember that no current actually flows through the gate in this direction. Okay, so the current is only flowing through the resistors R1 and R2 here, and there are also this drain current over here. Okay, and the current through these two resistors is IR1 comma R2. Okay, and IR1 comma R2 is equal to 10 volts divided by R1 plus R2. So this is equal to 10 volts divided by R1 plus R2, and then we have this value also, that IR1 R2 is equal to 0.025 milliamperes. And so from this equation we get the value of R1 plus R2 is equal to 10 volts divided by 0.025 milliamperes, which is basically equal to 400 kilo ohms. Okay, so we have the value of R1 plus R2 over here, which is equal to 400 kilo ohms. Now, the gate voltage VG is basically the voltage exactly at the junction of R1 and R2. So let me show you the picture again. So this the voltage at this point is basically VG, and VG is basically equal to R2 into 10 volts divided by R1 plus R2. Okay, or 10 volts into R2 divided by R1 plus R2. So VG is equal to 10 volts divided by R1 plus R2 into R2. Now VG is also equal to VGS, the gate to source voltage, plus the voltage drop across the resistor RS. So if you do not understand, let me show you this diagram again, that VG is equal to VGS, the voltage drop between the gate and the source, plus the voltage drop across this resistor RS. Okay, and it is given that VGS is approximately equal to VRS, and we have also actually solved for everything. So VRS is equal to 2.5 volts and VGS is also equal to 2.5 volts. So 2.5 volts plus 2.5 volts, which is equal to 5 volts. Okay, now we have the value of R1 plus R2, which is equal to 400 kilo ohms. So R2 is equal to 5 volts divided by 10 volts into R1 plus R2, and this is equal to half into 400 kilo ohms, which is equal to 200 kilo ohms. So R2 is equal to 200 kilo ohms and R1 plus R2 is basically equal to 400 kilo ohms. Okay, so R1 is equal to 400 kilo ohms minus R2 equals to 400 kilo ohms minus 200 kilo ohms, which is equal to 200 kilo ohms. Okay, so this is basically the solution of our problem. We have all the three resistors. R1 is equal to R2 is equal to 200 kilo ohms. RS, we have actually chosen this. This is equal to 5 kilo ohms, and W by L again we have solved for this problem. W by L is equal to 9.833. So equal to 9.833 over here. Okay, so this is basically the design parameters that were asked in this question. Okay, so let us do up to here today. Thank you everyone.